Welcome to this new lecture. In this lecture, we will learn scale image pixel data with keras. It means we scaling the pixel values of an image. The pixel values in image must be scaled prior to providing the images as input to a deep learning neural network model during the training or evaluation process. Keras supports data preparation for image data via the ImageDataGenerator class and API. Now first we see what is MNIST handwritten image dataset. MNIST handwritten image classification dataset. Before we dive into the usage of the ImageDataGenerator class for preparing image data, we must select an image dataset on which to test the generator. The MNIST problem is an image classification problem consists of 70,000 images of handwritten digits. The goal of the problem is to classify a given image of a handwritten digit is an integer from 0 to 9. As such, it is a multi-class image classification problem. The dataset is provided as a part of the keras library and can be automatically downloaded and loaded in memory by a call to the keras.datasets.mnist.load _data function. Now we see in the next cell load and summarize the MNIST dataset by using keras API. First, we import the MNIST dataset from TensorFlow. TensorFlow is a deep learning library developed by Google, and keras is API which is embedded in TensorFlow, and datasets package is already embedded in keras API, and MNIST dataset is our MNIST dataset handwritten digit dataset which we have to download. And then we import the matplot library for plotting the images or show some sample of images in this cell. Okay. Then first we load the dataset by using load _data function. Load _data function return four types of variables. The first two variables consist of train _images variable contains the training images, and train _labels contain the label of training images or classes of training images. And similarly, test _image variable store the all test images, and test _label store the labels of test images. So it means it return four variables. Next, we summarize the data shape. We use the shape attribute for all four variables to check their shapes, and then we summarize the pixel value. Train _images dot min function return the minimum pixel values of training images, and train images, and max function return the maximum value of pixel values of training images, and similarly dot mean function returns the average or mean of pixel values of training images, and STD means standard deviation function, it returns the standard deviation of pixel values of training images, and similarly we also applies these function on test images. And the next part of code shows some images of MNIST, shows some sample of MNIST images. For example, we draw first 20 handwritten images of MNIST dataset. This is the subplot. Its mean 2 means 2 rows, and 10 means 10 columns. So it's mean we show or we display here that first 20 images of MNIST dataset. And ImShow function show the image, and title show the label of a specific image. So run the cell and see our output. Okay, downloading. Yeah, downloading is this line shows downloading is completed. This is the shape of training images. Shape mean this is 60,000. 60,000 mean total number of image in training. That in training part is 60,000. It means training images. Trainings variable contain 60,000 images. 28 is the height of image, and this is the height of image, and 28 pixel is the width of image, and therefore 10,000 images, 10,000 test images. 28 is height, and this 28 is height, and these are the number of labels. Please keep in mind the number of images and the number of labels in a data set always equal, and this is the minimum value of pixel value, which is 0, and the maximum value of pixel in an image is 255, and similarly same for test images. And then we see this is our images, which is handwritten digits, and these are the sample images, and these are the label of images, and it's mean this is 5, and this is 0, and this is 4, and this is the whole output of our above cell. So we go in next. ImageDataGenerator class for pixel scaling. It's mean now we study the ImageDataGenerator class, which is already exist or developed or embed in the Keras API. The ImageDataGenerator class in Keras provides a suite of techniques for scaling pixel values in your image dataset prior to modeling. Modeling means to train any modeling. The class will wrap your image dataset. Then when requested, it will turn images in batches to the algorithm during training, validation or evaluation, and then apply the scaling operation just in time. This provides an efficient and convenient approach to scaling image data when modeling with neural networks or convolution neural networks. The use of the ImageDataGenerator class is as follows. First, number 1, load your dataset. Number 2, configure the image data generators, mean construct an instance of ImageDataGenerator class. Number 3, calculate image statistics, call the fit function. Number 4, use the generator to fit the model. It's mean pass the instance to the fit_generator function. Number 5, use the generator to evaluate the model. For example, pass the instance to the evaluate_generator function. Next, the 3 main types of pixel value techniques supported by the ImageDataGenerator class of Keras API are as follows. For number 1, pixel normalization. In pixel normalization, we scale pixel values to the range 0 to 1. Number 2, pixel centering. Scale pixel values in such a way to have a 0 mean. Pixel standardization. Scale pixel value to have a 0 mean and unit variance. Next, now we normalize the image by using the ImageDataGenerator class of Keras API. The ImageDataGenerator class can be used to rescale pixel values from the range of 0 to 255 to the range 0 to 1, which is preferred for neural network models. Scaling data to to be range of 0 to 1 is traditionally referred to as normalization. It means the process of converting image data from 0 to 255 in the range of 0 to 1 is called normalization of image data. This can be achieved by setting the rescaled argument to a ratio by which each pixel can be multiplied to achieve the desired range. Desired range means range 0 to 1. In this case, the ratio is 1 by or 1 divided by 255 or multiply about 0.039. So, example of normalizing or rescaling pixel values start from here. First, run this cell so that dataset is load and ImageDataGenerator class is import. Now again we load dataset of MNIST digit handwritten digit dataset, and in next cell we reshape dataset to have a single channel. Now we declare, for this we declare three variables: width, height, channel, and then we got the values of these variables: train x dot shape dot of shape 1 attribute and train of 2 and then 1. Okay, then we reshape the dataset to add the channel attribute or channel value. So run the cell and then we see what is the effect of this code on our image dataset. Okay, there is some problem in the code. Okay, this is a actually problem. Shape okay, sorry, first download the dataset and then run this. Okay, now we have a downloaded dataset, and you can see in the previous cell there is this is the shape of our dataset, and in its mean there is no channel is absent here, and then in this dataset we had added the channel of the image. Channel means actually a grayscale image has channel 1 and a color image which consists of RGB format is channel 3. So the grayscale image have channel 1. It means it depends on one colors. Okay, next confirm the scale of pixels. Now we see the maximum and minimum values of pixel values in training images and also in test images. So run this cell. So this is the minimum value and this is the maximum pixel values in the image. Next we create a instance or object of ImageDataGenerator class, which is DataGen, and we set the image and we set the parameter of ImageGenerator class as it is 1 divided by 255, and we run this cell. So now our images have our pixel values of our images has scaled from 0 to 55 to 01. It means now each maximum pixel value is now converted is 1 and minimum is 0, and then other values between 0 and 1. So run this cell and okay. Next we fit this in first we load our training images and labels in DataGenerator class training underscore iterator. Test underscore iterator is mean 1 by this mean DataGenerator class apply each image of train x and each image of label, and then set the batch size of images 64. It's mean it batch underscore size, batch of images means we divide our data set in 64 in group of 64 images. It means total images divided by 64. So run the cell. Okay, now we convert our data set, our images of our training data set into batches with 64 batches of images. It means first batch is 64, second batch also 64, and so on. And we minimum value of 0.0 and the maximum value is 9.0. Center images with image data generator. Another popular pixel scaling method is to calculate the mean pixel value across the entire training data set, then subtract it from each image. This is called centering and has the effect of centering the distribution of pixel values on 0. That is, the mean values for centered image will be 0. The image data generator class refers to centering that uses the mean calculated on the training dataset as feature-wise centering. It requires that statistic is calculated on the training data prior to scaling. So we again import the MNIST dataset and image data generator class from keras API, and then again we load the MNIST dataset by using load underscore data function. So we run this cell, and again we reshape our dataset by adding a channel color channel into image dataset. Okay, report per image. Actually, this is the mean value of training images, and this is the mean value of test images. Pixel values of test images and pixel values of actually this is the mean of pixel values of training images, and this is the mean of pixel values of test images. Okay, create a generator that center pixel values. Now we again create an instance of image data generator class and feature underscore center parameter set to true. Okay, and then run these cells to fit this data generator class on training image. You can see this in this output and this output is the same, but this is we use another method, and this is used by image data generator class. Demonstrate effect on a single batch of samples. So for this we run the cell. Okay, then get a batch. When you want to get a one batch of all batches of your images dataset, then you can use next function. This returns the one batch of images, and then also the mean pixel values of the 64 images, mean first batch of images. Okay, now we apply the above operation on all training dataset. So run the cell. Okay, run the cell, get first batch. Okay, print the shape up. Okay, now this is the mean value of our all batches, and this is our whole dataset. Okay, next, standardize images with image data generator. Standardize is a data scaling technique that assumes that the distribution of the data is Gaussian and shifts the distribution of the data to have a mean of 0 and a standard deviation of 1. It means we normalize the images by using Gaussian distribution formula, which is a popular statistics formula. Data with distribution is referred to as standard Gaussian. It can be beneficial when training neural network as the dataset sums to 0 and the input are small values in the rough range of about -3.0 to 3.0 of the values will fall within 3 standard deviation of the mean. Standardization of images is achieved by subtracting the mean pixel value and then dividing the result by the standard deviation of the pixel values. So we do practically standardization of images in this cell. Example of standardizing image dataset. First we import the MNIST dataset and then we import the ImageDataGenerator class from keras API. Then load the dataset by using load_data function. Then we reshape dataset to have a single channel. Okay, and report pixel means and standard deviation. Okay, these functions we have already studied in the previous code cells. So next create generator that center pixel values and then set image generator class parameter of image generator class or feature underscore center true and feature underscore standard deviation normalization true. It's mean this features, when we set this feature as its value true, then it's mean it is applied the Gaussian formula on our data set. So run the cell. First run this cell and then this. Okay, the mean is 33 and standard deviation is 78. Demonstrate effect on a single batch of samples. Now we run this cell to achieve our required result. Then get a batch of image by using next function and then pixel stats in batch. So in batch, this is the shape of our batch and this is the mean of pixel values of our whole batch and this is the standard deviation of our batch. Next, now we apply on entire data sets. Okay, get a simple batch and then now on our whole data set the standardization process is completed. So thank you very much. See you in the next lecture of computer vision with deep learning.